Okay, so you'll notice in part one of this course, we go through the subjects rather quickly, and you'll see that things kind of slow down a little bit, and are more, sort of our description of how organs work is a little bit more lengthy. So we're moving right along from epithelial cells to excitable tissues. And again, we've got 4 tissue types. Connective we don't talk about, epithelia we've already covered, and we're moving on to muscles and nerves. And what do I mean by an excitable tissue? Well, both muscles and nerves are excitable because they change their voltage, the membrane voltage, in response to stimuli. So they have that in common. So some of what I'm going to explain about neurons, we can apply to muscles. And so we'll do it in that order. So the first question is, how is a potential established? What do I mean by potential? Anybody know?
Like, when you say potential, isn't it like pre-voltage or something like that?
It's a voltage, yeah. So we'll just treat it as a synonym. So it's not necessarily potential energy, although you could argue it's a source of potential energy. When I use the word potential, I'm referring to voltage, and in particular, the voltage across a membrane. So we already talked about how neurophysiologists will implant a little piece of glass, a microelectrode, into the body of a cell, and they'll have another electrode on the outside for reference. Those kinds of recordings are what we're referring to. So the first question is, how do we do that? How do we create a voltage across a membrane? And then the second would be, how does that change? Okay, because it's really change that matters. These voltages that we can measure are a source of information that's transmitted through the body quite rapidly and allows for the activation of muscles. All right, so first question, how is a potential established? So we have this very simplistic model of a cell with lots of sodium on the outside, potassium on the inside. We've got proteins which have a negative charge, and there might be a little bit of chloride as well. And the recording across the membrane, again, using these little pieces of glass, might look something like this. It's going to have at rest a negative value. And we call that measurement, let's just say this is a real cell, we call that measurement the membrane potential. Okay, so it's the membrane's voltage. All right, so in particular, we're going to first focus on neurons, okay? And the question is, how do we model this? Okay, what are, the physics are actually pretty straightforward. The chemistry is fairly straightforward. And so this seems like a simple enough system that we should be able to devise a way to measure the properties of this internal chemistry, these proteins, if we could count them all up, and these ions on the interior and compare that to the exterior. How do we calculate this particular value for the membrane potential? Well, what's one factor that seems should matter? What should matter? I'm posing it to you guys. How about people not in the front row, because you guys have been answering everything. I want folks back there. What matters in this system? We want to know, what's the voltage? What should matter to the voltage? Raise your hand. Yeah.
Charge.
Excellent. Charge, right. Positive or negative? Seems like that should matter. What else? Yeah.
The degree of difference between positive and negative.
The,
One side is more negative, the other side is more positive.
yeah, more positive, more negative. How maybe could you measure that, you think?
Electron transfer?
Maybe actually, so for the motion is going to be important later, but let's just treat it statically. Anybody know? Just like it's a way that might be measured to quantify that? How about, yeah?
Concentration of potassium.
Exactly, concentration. So it's the relative concentration of the interior compared to the exterior, right? Because it's a voltage, and it's a differential measurement. We're comparing a separation in charge across the membrane. And so, so it's the relative concentration that matters. And the way that it's done is just the convention is the exterior goes on the numerator, the interior of the concentration goes on the denominator. And when I use the word ion here, you could plug in any particular ion, but it has to be the same one between the numerator and the denominator. So we could be talking about potassium. Charge, that's going to be a factor. And then there's other physical constants so that we go from a concentration, and actually this is a ratio concentration, so it's non-dimensional. And then on the left-hand side of our relationship, we want to have millivolts or volts. And so we need constants in there that convert a concentration difference and take the charge, which also doesn't have units, and turns it into something that's dimensional. And so if you really know your physics, you could figure out that the gas constant factors in there, the temperature of this solution, and so that's going to be our body temperature, the Faraday constant, and then on the denominator we have the valence or the charge. And then there's another constant in there, 2.303. All right, now it's really the difference in concentration by orders of magnitude that matter in this relationship, okay? If you just have a twofold difference in concentration, it's not terribly important, but if you have a 100-fold difference in concentration, then it really matters to the voltage. And so that's what the 10 base log does for us. And so, so it's reflecting how different the interior and the exterior is in orders of magnitude. That's it. That's the whole equation. There's some ugliness here, but fortunately, these are all constants, and basically we're talking about body temperature, so this just boils down to a value of 61. And we set that equal to this voltage. So this is a beautiful model, okay? You only really need to know the valence and the concentration difference of an ion to predict how it's going to affect a voltage. And so it's a big deal. So it's again named after a long deceased investigator, Nernst. It's the Nernst equation. And the Nernst equation gives a prediction of voltage. And it's a very particular type of prediction. We call it the equilibrium potential. Notice only one ion is in this equation. And so this is a prediction of the membrane potential you would get if only one ion mattered. Okay, it's the membrane potential from one type of ion. So you can calculate an equilibrium potential for potassium, you can calculate one for sodium, one for chloride, one for calcium. If I know my concentration, I know the charge, this is what the membrane should be if only that ion matters. So you can do that calculation. So again, all of those constants boil down to a value of 61. So we can restate the Nernst equation a little bit more simply as 61 times the 10 base log of a concentration difference. And if you do that for potassium, this is the convention. You say, instead of E sub ion, it becomes E sub K plus. These are reasonable concentration differences, again, the outside being less than the inside of the cell. Those are realistic values, and so if you plug those in, then you get an equilibrium potential for potassium of minus 90.3 millivolts. Okay, so that by itself doesn't seem all that meaningful, but if you do that calculation for sodium as well, you find that sodium gives you a really positive number. Huh. Well, okay, so one question, somebody actually came up at the end of last lecture and posed this question, which is a great source of confusion for people. How can it be that these two ions, which have the same charge, create a situation where one of them has a negative voltage and the other one creates a positive voltage? How do you have potassium create a negative voltage? Does anybody know the answer to that? Yeah?
Because there's more potassium inside the cell.
There's more potassium inside the cell, right. I don't know if you guys remember from last time. Yeah, another question?
I think it's negative because I think how the Na plus K plus transporter works is it moves two positive charges in for every 3 that fill out.
Right. Yeah. So again, that sort of that works with what he said, which is that you've got the sodium potassium ATPase, which creates the concentration difference, and it's the concentration difference itself that explains this negative voltage. Another point.
Is it the Nernst equation kind of gives you clues about like spontaneity, right? About what will spontaneously flow inside and out. So like if it's negative, it won't, like the A is not going to flow in a direction, right, passively.
Well, not necessarily. So you can just look at the concentration, and you can ignore any factors that might be governing that concentration. And that's actually a good point to raise as well, because you've got things like the negatively charged proteins in the interior, and they're going to attract potassium. But notice there's nothing about protein in the Nernst equation. This is what's so elegant about it. There's nothing about sodium in the Nernst equation, which is going to tend to repel potassium. All that matters at the end of the day is that concentration difference. So those might be important factors, but they are not necessary for you to do the calculation and understand how you get this equilibrium potential. So just to complete the thought on the concentration difference, I mentioned last time that there's this convention. If you want to know, should my voltage be positive or negative, ask the question, well, what happens to charge as I go from the interior to the exterior of the cell? And so for the Nernst equation, we're always focused on just one ion. So we can pose that question just for potassium. So we've got a lot of potassium on the interior, not so much on the exterior. So as we go from inside to outside, you'll see we go from a situation with lots of positive charges to fewer positive charges. That means a negative voltage. We have a drop in the positive charges, okay? Whereas sodium is exactly the opposite. For sodium, we go from a low concentration, very few positive charges on the interior. Then we move from inside to outside. We have a jump up in positive charge. Therefore, sodium yields a positive equilibrium potential. The way that works out mathematically, it just has to do with whether or not your ion is on the numerator or the denominator. If you flip them around, you get you'd get a flip in whether or not your number is positive or negative. But you can think about it mathematically, or you can think about it in terms of charge from the inside to the outside of the cell. Okay, so the bottom line is, it doesn't matter, the valence of your ion doesn't dictate the sign of your voltage. You can have negative chloride create a positive equilibrium potential or a negative equilibrium potential. It just depends on the relative concentration of that ion across the membrane. Question?
Yeah, are these charges like additive? So to like find the overall charge of the cell, you just like add these two together?
That's a perfect question for my next topic. So are they additive? How do you interact? How do you account for the different ions? So before we get to that, let me just point out how these numbers compare to what you would actually measure on a live neuron. So if you actually perform this experiment and you got a reading, then to which ion do you think that membrane would come closest? Just you can mentally answer that question, and then you do that experiment and you see that you get a value. This is not the equilibrium potential, which would only be generated by a single ion, but just to get to your question, this is a consequence of all potential ions and all protein. This is what you get when you perform the measurement. And so we see there's a difference between this model of the membrane, the Nernst equation, and our measurement. Neither predicts the measurement, but the measurement is a lot closer to the equilibrium potential for potassium than it is for the equilibrium potential for sodium. So it seems like, okay, potassium sort of seems like a better version of this model. It's closer to potassium than to sodium by far. So the question now is why? Why is that the case? So this is going to answer your question. Another sort of observation or hypothesis would be that some ions seem to matter more to the membrane potential than others. So why is that the case? What is it about potassium that allows it to influence the membrane more? Any guesses? Hypotheses? Yeah?
Does it have to do with how many like orbitals or how many electrons it has in its orbital?
Good guess, but no, it's not about electrons. Yeah?
Is it like size? So use it.
About size? No, we'll treat both ions as very tiny. Any other guesses? So potassium seems to matter more. Why is potassium more effective at affecting the membrane than sodium? Yeah.
Because it takes energy to move sodium against the membrane.
The hypothesis has to do with energy and the transport, the energy requirements. That's not true, but it's another good hypothesis. They're both being driven by sodium-potassium ATPase. Yeah, another one?
Are there more potassiums in the environment than sodium?
More potassium. Okay, so one hypothesis could be that the concentration difference is bigger, maybe. But actually, that's already encapsulated by the Nernst equation, because the Nernst equation is all about the concentration difference. And so one thing you can see here is that actually potassium, 90 and 60 are not hugely different numbers, and so they reflect the relative concentration difference, even though the sign is different. One's big on the inside, one's big on the outside. But you can see that there is a concentration difference that's reflected in the equilibrium potential, but it's already there. That already shows us something about concentration. So there's some other property that matters here. And actually, I sort of misled you because it's not an inherent property of potassium or of sodium, but it's a property of the membrane. This property is essentially favoring one ion type against the other, and that property is its permeability. Okay, so whether or not a membrane is leaky or permeable to an ion is going to dictate its influence, that ion's influence on the membrane potential. And so what we have to do with it, there's nothing about that in the Nernst equation. The Nernst is a very simple model of the membrane. We need to elaborate our model in order to account for this permeability effect. Okay, so we take the Nernst equation, and now we're going to add a parameter to it. It's really a variable. The permeability. Now, if that was the end of it, then the p's would just cancel out and you could be right back to the Nernst equation. But instead, what we can simultaneously do is factor all ions that matter to the membrane. And those tend to be potassium, sodium, and chloride. We'll see when we talk about muscle cells especially, calcium's a big player, smooth muscle, calcium's a big player. But for neurons, these are the big players. So this is no longer called the Goldman equation, but it's no longer called the Nernst equation, but it's called the Goldman-Hodgkin-Katz equation, shortened as the Goldman equation. We'll give Goldman most of the credit. And just to think again about this discrepancy between potassium and sodium and how they affect the membrane potential, I'll tell you that at rest, potassium has 40 times the permeability, or the membrane is 40 times more permeable for potassium than it is to sodium. So just right off the bat, that P in front of the K is 40 times the P that goes in front of the Na concentration difference. And that explains why potassium has such a hold over the membrane potential.
I have a question.
Yeah, question.
Why is the Cl on top in and then it's out in the bottom?
That's an excellent question. Why is it? The question is, why is it that we've got this convention where potassium's the outside concentration is on the numerator, whereas when you look over at chloride, it's the interior concentration that goes on the numerator. Anybody know why that is?
Can I guess?
Yeah.
All right. Like what you said before about sodium yields a positive equilibrium potential because there's more sodium on the outside of the neuron. Does that have to do with the fact that there's more chlorine on the inside?
Almost. So the reason, yeah.
Is it because that's the opposite effect because negative?
Yes, that's correct. So for those that couldn't hear that, the reason why you have a difference in chloride being on the numerator or the denominator is that chloride is the only one that has a negative valence. And so again, it's, when you take the 10 base log of a situation where you've got a bigger number on the denominator, that yields a negative number, right? And so, so the reason for that flipping has to do with whether or not it makes sense as you go from the interior to the exterior of the cell, given a concentration difference in something that has a negative charge. Notice that we've eliminated valence, which was outside of the 10 base log in the case of the Nernst equation, and now it's incorporated in whether or not the numbers are on the numerator or the denominator.
Thank you.
Yeah. Okay, so how is a potential established? We've got the Nernst equation, which tells us that it tells us how concentration differences and the charge of an ion determine the equilibrium potential. So you really want, when we talk about how neurons work, you really want to think clearly about equilibrium potential. Make sure you understand that this is fundamental. What is the difference between equilibrium potential and membrane potential? Okay, equilibrium potential is how one ion is influencing the membrane. The membrane potential is how all ions and charged particles are affecting the membrane. So Nernst is only for one, whereas Goldman considers all. It's a model for how all ions are affecting the membrane. And what we have to incorporate into that, in addition to considering 3 ions, we now have to factor in permeability. The permeability dictates how close the membrane potential is to the equilibrium potential of a particular ion. Dramatic pause. Okay, so the next question is, how does the potential change? Thus far, our model is for a static membrane. And we've created a situation where we have concentration differences, we have a little bit of permeability, but it's basically a static system. And we've only explained the resting membrane potential. Whereas these excitable tissues are all about changes in membrane potential. So to begin to think about that, we can return to the Goldman equation and just imagine a scenario where these permeabilities are not fixed constants, but they are variables that are dynamic. And so just consider the permeability of sodium, which we have on the top graph. And I'm going to show you lots of graphs that look like this, where we've got time on the x-axis, and we've got some kind of variable on the y-axis. Okay, and so sometimes one of those variables influences another one of those variables, and that's the case here, where we're going to impose changes in permeability of sodium. So again, that's up here in the Goldman equation. That's what we're changing. And then we're asking the question, well, how does it affect this, the membrane potential, the stuff on the left-hand side of this equation? So we start off with a relatively low permeability for sodium. And we see that, yeah, we've got the resting membrane potential right there. Okay, it's flat. And we're going to impose a rather unrealistic, very rapid change in permeability. And when we do that, we see that eventually there's a little bit of damping in the signal, but eventually the membrane potential follows suit and also rises. And what is it going to rise to? What should the, let's just say we totally open the floodgates so that sodium permeability is dominant. That is, this membrane is leaky for sodium like no other ion. Then what should the value of the membrane potential be? If I draw a dotted line here for what this value is, what is it going to be? Raise your hand. Yeah. It's going to be positive? Yep. Positive 60. And why is it positive 60? That's the equilibrium potential for sodium, right? So the Goldman equation would give us that value of plus 60 if we somehow knew the concentration of sodium inside and outside the cell. So what this shows us is that if we make, not only does permeability matter in a static situation, but if you can change permeability, then you can get the membrane to then move towards the equilibrium potential for that ion that you're making the membrane permeable to. Okay, and if you really open it up and you keep it open, that eventually the membrane will just settle in at the membrane potential, or at the equilibrium potential for that ion. In this case, it's the equilibrium potential for sodium. So that rise in permeability causes the membrane to move towards that equilibrium potential. How do we drive these changes is the last point I'll make. How do we drive changes in permeability? Okay, we've talked about leakiness. Again, that's good for a static situation. But if we want to change it, how do we dynamically change a membrane? That's where we have gated ion channels. Okay, so we talked about channel proteins. I mentioned that there were leak channels that are just fixed pores, but there's the opportunity to have a more sophisticated system, which is a gated channel. And they're gated in 3 different ways. The first one is that they grab onto a molecule called a ligand. That makes it ligand gated. Secondly, if they are exposed to tension in the plasma membrane, that's known as a mechanically gated channel. And then finally, we have voltage gated channels. The channel itself is sensitive to the membrane potential, and it will change its permeability according to that membrane potential. So that's what, yeah, question?
What was the ligand gated again?
Ligand gated, so a ligand is a chemical that binds to the channel. So a ligand is, just think of it as the chemical that matters to trigger it. And when it binds to that chemical, then it opens up. Okay, so we'll pick this up next time.